Continue on physical chemistry, chapter 3. We're beginning section 2 now. Let's talk about heat engines. Now we're going to call tau, this symbol here, tau, a generic temperature scale. It doesn't matter if it's kelvins or whatever. So we're going to have a hot reservoir here. It's going to be at the temperature H for hot, obviously. And then we're going to have our system, and then a cold reservoir at a different temperature, C for cold, obviously. We're going to have our system doing work. So heat is going to come from the hot reservoir into our system, and some of it's going to go, some heat is also going to go into from the system, the cold reservoir, and then hopefully we can get some work output. Now remember, positive work would be doing work on the system. So we write minus W to show the system is doing work done by the system. So our system is absorbing heat from the hot reservoir, it's releasing heat to the cold reservoir, and it is doing work. Now the engine inside has got some sort of working substance. This substance somehow it takes heat and it performs work. Now this is a closed system. Remember, that means matter can't get in or out, but energy can. Now in a nuclear reactor, I've heard this is actually molten sodium, etc. In a refrigerator, it might be something more like ammonia. I think they actually have newer chemicals these days, but whatever. Now for this heat engine then, the Q hot coming into the system is greater than 0. The work is less than 0 because the system is doing work. And then QC is less than 0 because the system is losing heat that way to the cold reservoir. Now we're going to use lowercase e in this context to represent the efficiency of the heat engine. Now this is the same e as in, the anti-log of, natural log of e or whatever. So don't get confused. Pay attention to context. So we're going to say the efficiency is the work output divided by the energy input. Now the work output we showed on the graph is the minus W, and the energy input is the heat from the hot reservoir. Now that's obviously going to be a negative quantity. Well, technically, yeah. So we're going to show an absolute value just because we actually want a positive number here. So we're going to basically take the absolute value of work divided by the heat coming from the hot reservoir. So this will give us a positive efficiency. We don't want to talk about negative efficiency. That wouldn't make any sense. This ratio then is going to be greater than 0 but less than 1. Now for a cyclic process, remember U is a state function, therefore the change in U is going to be 0. And remember, the first law states that Q plus W is equal to delta U. So Q plus W is going to be the QH plus QC plus W is equal to 0. Now, solving for minus W, then we get minus W is equal to QH plus QC. That's for the cycle. For one cycle or a multitude of cycles. For solving for QH, then we have minus W, the work, plus minus QC, the heat going to the cold reservoir. So what this is showing is that the heat coming from the hot reservoir gets split two ways. Some of it becomes work, and some of it becomes heat going to the cold reservoir. It'd be nice if this was 0, but that can't happen. Remember the second law. Now here's an example of a machine that violates the second law. Heat reservoir, heat goes into the cyclic machine, our system, and then work output equals Q, this Q up here. I probably should have labeled that. Q. There. Minus W. So Q coming in the system and then minus W coming out. Now, there is experimental and theoretical evidence of the second law. For example, the ocean. It's not absolute 0, right? It's got temperature. So why can't we, and it's huge, so why can't we just take the ocean, get heat out of it, and use a machine to drive work? Of course, if we did that forever, we'd freeze the ocean solid, but you'd get the idea. Don't worry about the ocean freezing solid. This is impossible. Now, another evidence, let's say we have the derivative of pressure with respect to temperature, and that's equal to the change in the enthalpy of vaporization divided by T delta V. That should be a nice V down there, not a U. So V is volume, going to liquid to vapor. Now, this can't be derived using the second law. Okay, so delta V, the change in volume would be the volume of the gas minus the volume of the liquid. Actually, I can't remember what that has to do with the second law, darn it. Okay, so let's talk about, okay, so the first law says you're not going to get something for nothing. You can't win. The second law says you can't even break even. These refer to converting energy, specifically converting heat to useful energy. So let's continue to talk about the efficiency of a heat engine. We already said the efficiency is minus W over QH, and that the minus W is QH plus QC. So with the E is QH plus QC over QH. Common denominator, so we could just say E is equal to 1 plus QC over QH. Now QC over QH has to be less than 0. Remember, QH is going to be positive, QC is actually negative. So obviously the ratio there, the fraction is negative. So like I said, the heat going into the cold reservoir is less than 0, and the heat coming out of the hot reservoir is greater than 0. So if you take this 1 and add a negative number, you're going to end up getting a number less than 1. So energy, or the efficiency, is less than 1 for a heat engine, based on the assumption that tau hot and tau cold will not change during the process. Also, of course, tau hot has to be greater than tau cold. Now let's talk about the Carnot cycle, or Carnot's cycle. This is way back in 1825. So E, remember, is the efficiency of any engine working between tau hot and tau cold. Now the efficiency of a reversible engine is just E subscript ReV. Now remember, E has to be less than or equal to the efficiency of a reversible engine. That is Carnot's principle. So what that means is you can't have some sort of weird super engine with the efficiency greater than or equal to the efficiency of a reversible engine. Remember, reversible is an approximation. For example, if your system is going to have moving parts, so you can make it with as few moving parts as possible, but you can't make it without moving parts, or you don't have a system. And likewise, you could try lubricating moving parts, blah, 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 but you're not going to do anything. So see handout 10. So now, what happens if you couple two reversible engines together? So you're going to have one big hot reservoir shared between the two. You're going to have one big cold reservoir shared between the two. You're going to have reversible engine A and reversible engine B. Now, what we've shown here then is that reversible engine A is the one that's going to move what you call forward. It's going to take hot heat and do work and give off waste heat. And the reversible engine B is the one actually going in reverse. Work is coming into it, and it's actually pumping heat out of the cold reservoir and putting heat back up in the hot reservoir. Now remember, if we could reverse it though, right? If we do the diagram as shown, we know that based on Carnot's principle, that the efficiency reversible engine A has to be less than or equal to the efficiency of reversible engine B. But if we were to drive these the other direction, with B doing all the work and A pumping it backwards, then we would have to say that based on Carnot's principle, that the efficiency of reversible engine B has to be less than or equal to the efficiency of reversible engine A. The only way these two are not a contradiction is if we end up with the efficiency of reversible engine A equal to the efficiency of reversible engine B. So our conclusion is all reversible heat engines operating between the same two temperatures must have the same efficiency. The efficiency of a reversible engine is the maximum efficiency possible for any heat engine that operates between these two temperatures. Now remember, the efficiency of an irreversible engine has to be less than or equal to the efficiency of a reversible engine. And efficiency reversible is theoretical anyway. Now, this conclusion, we've been using PV work as an example, but it's not necessarily true. These conclusions are all true even if our work is not pressure volume work. For a power plant, water is the cold reservoir. This is why they always big nuclear power plants and other big power plants along rivers and so on, so they can get a huge supply of cold. Now, real-life power plants, they're about 0.4 to 0.6. E is about 0.4 to 0.6. So it's not as close to 1 as we would like, but this is a lot more than 0. Now, one thing though, the efficiency of a heat engine is independent of a couple things. One, the nature of the working substance. And two, the kind of work. Doesn't matter if it's PV work or non-PV work or what. Now, how do we calculate the reversible E, efficiency of a reversible engine? Well, the efficiency reversible, of course, based on what I showed you with Carnot cycle, should be a function of the hot tau and the cold tau. Remember, this tau means any temperature scale. Now, thermodynamics uses the ideal gas scale, which is fictitious. So here we go. So we're just going to say tau C is going to be equal to Tc, capital T is temperature, and tau H is equal to Th. So T is the ideal gas temperature scale, kelvins. So here's how the details of how a Carnot cycle actually work. We're graphing pressure against volume, and we have 4 steps, 1, 2, 3, 4, and then back to 1. So you have the Th, this is at constant temperature here, and then you come down here, and then you go back up at Tc, and then you go back up here. So step 1 to 2, this is isothermal expansion. We are doing work, and QH is greater than 0. Step 2 to 3, this is adiabatic expansion. Temperature will change. Obviously, it will decrease. Step 3 to 4, this is isothermal compression. This is the part where QC is less than 0. We're releasing the excess heat into the cold reservoir. And then 4, adiabatic compression. And that's where we come back to where we were before. Now it's important to realize that the heat, from step 1 to 2 is not necessarily the same as the heat from 3 to 4. In fact, they should be different. If they were the same, you've done 0 work. Now remember the Carnot cycle then, you can see from this graph, is 2 adiabats, 2 isotherms, all done reversibly. Now this is assuming, of course, we're only doing PV work and we're working on a perfect gas. You could do anything else, of course, just the math will be more complicated. Now the first law said that the differential of internal energy is equal to the differential of Q plus the differential of work, which is dQ minus PdV, since dW is equal to minus PdV for a reversible process, assuming, PV work only. We also know that du is equal to heat capacity constant volume times the differential of temperature. So we get CV dt is equal to dQ minus PdV. And then CV dt is equal to dQ minus nRT over V. So we substituted in nRT over V for P, dV. That way we have the same variables over here and we can integrate or whatever we're going to do. So this is for a perfect gas only. Now what we're going to do is divide that by temperature. So we have CV dt over T is equal to dQ over T minus nRT over Vt dV. Now, these T's can cancel because T is not equal to 0. The third law of thermodynamics says the temperature cannot be 0. So we're free to cancel those T's out. If the T wasn't 0, remember, then you got 0 over 0, and don't do that. So we're going to integrate, we're going to find the integral of this whole equation, a cyclic integral over one whole cycle. So we have the cyclic integral of the heat capacity at constant volume, which is temperature dependent, dt, divided by T. And that's equal to the cyclic integral of dQ over T minus the cyclic integral of nR over V dV. Now remember, the cyclic integral is a closed integral or a line integral. Now, so the cyclic integral of nRV over dV is equal to 0 because V is a state function. So V is going to end up where we started and where we end. Now the closed integral of a product of a state function is 0. So the cyclic integral of PV is equal to 0. So now the cyclic integral of the differential of the natural log of V is equal to 0, also because V volume is a state function. Also, the cyclic integral of the differential of internal energy is equal to 0, also because internal energy is a state function. Also, the cyclic integral of dV over V is equal to 0, since V is a state function. Also, the cyclic integral of CV of t over t dt is equal to 0. So now, what we end up with, the cyclic integral of CV of t over t dt is equal to the regular integral from temperature 1 to temperature 2 of CV of t dt over t, plus the integral from T2 to T3 of CV of t over t dt, plus the integral from T3 to T4 of CV of t over t dt, plus the integral from T4 back to T1 of CV of t dt over t. Now, remember, these are 4 regular integrals. Their total sum is the cycle. Their total sum is equal to 0. Just because their total sum is equal to 0 doesn't mean each one is equal to 0. In fact, what we do know is going from T1 to T2, that was isothermal. Therefore, the integral of that is 0, because we're integrating with respect to temperature. Likewise, the integral from T3 to T4 is isothermal. Therefore, its integral is also 0. So T2 to 3T, if the part from T2 to T3 and the part from T4 to T1, all this adds up to 0, and these two are 0, then these two cancel out. They're equal but opposites. So we can say that the integral from T2 to T3 of CV of t over t dt is equal to the integral from the hot temperature to the cold temperature of CV of t dt over t. And that's equal to minus the integral from Tc to Th of CV of t dt over t. So we get the integral from T4 to T1 of CV of t over t dt is equal to the integral from Tc to Th of CV of t over t dt. Now remember, so what that leaves us then is that the cyclic integral of dq over t is equal to 0, which means this quantity here is some sort of state function. Now that should be interesting because t is a state function, but we know that q is not, and the differential of q is not. Yet somehow this quantity together is a state function. Now the cyclic integral of dq reversible over t, that's going to be the integral from state 1 to 2 of dq over th, plus the integral from state 2 to 3 of dq over t, plus the integral from state 3 to 4 of dq over tc, plus the integral from state 4 back to state 1 of dq of t. And that is equal to 0 because we just showed us the state function. Now from steps 1 to 2 and 3 to 4, temperature is constant because we're the temperature of the hot reservoir here and the cold reservoir here. So integrating that will be easy now. Now for steps 2 to 3 and 4 to 1, we know that Q is equal to 0 because those are the adiabatic steps, adiabats. So what that leaves us is that the cyclic integral of dq over t is equal to 1 over th times the integral from state 1 to 2 of dq plus 1 over the cold temperature times the integral from state 3 to 4 of dq, and that's equal to 0. So integrating those, we get qh over th plus qc over tc is equal to 0. So just moving them to opposite sides, what we end up with is that the heat going into the cold reservoir divided by the heat coming out of the hot reservoir is equal to the negative of the temperature of the cold reservoir divided by the temperature of the hot reservoir. That has to be absolute temperatures, though, obviously. The thermodynamic temperature scale is what we're talking about. So remember, we said the efficiency of a reversible engine is 1 plus QC over QH. So this is the heat coming out of the system going to the cold reservoir, and this is the heat coming out of the hot reservoir coming into the system. And that's equal to 1 minus, substituting in, TC over TH. Or, common denominator, TH minus TC over TH. So now we can say that the efficiency of a reversible engine is equal to 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. And this is true for any working substance. So what this tells us then is that a hot temperature makes our system more efficient, and then a lower cold temperature also makes the system more efficient. Now, in practice, of course, that can be dangerous. We can't just make the hot temperature super hot, or we'll have to, deal with increased pressure and all sorts of stuff and cause problems. In a cyclic integral, if a cyclic integral is equal to 0 of a quantity, then remember it's a state function. That's the end of section 2.